Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz, and I'm glad that you have taken the time to join us today as we look at our topic of how to choose torque wrenches and screwdrivers to improve quality. Now, if you've been with us for any number of our webinars, we usually start with highlighting some of the fastening risks that come with the assembly process. And one that is primarily a culprit is going to be the over torque situation. And that typically causes issues because our real goal is creating the correct clamp force to hold our components together. And if we try to go over the recommended torque, then the fastener itself could stretch past its yield point, and then any shock or vibration can cause that fastener to fail. And then we have issues. Now, conversely, that is if there's a fastener that's under torqued. And again, we have any type of shock or vibration that can cause that fastener to back out, and then also creating failure as it's not holding the components together that we need to keep together. Also, material breakage can happen. That would be typical if there was an over torque situation, and maybe the components themselves don't necessarily handle any type of over torque threshold, and those materials can break if the operator is not necessarily paying attention. And this can really happen in maybe a self-tapping type of scenario. And that's always going to create downtime and rework, which is costly and time wasting. And then any type of safety critical joint is going to require special tools that if our human operators aren't necessarily paying attention with these safety critical areas, there can be real problems where people can get injured, hurt, or worse. And that is all due basically to a lack of an error-proofing process for that safety critical application. And so when we look at torque control, our main goal, as I mentioned, is to create the correct clamp force. The ideal way to handle that currently right now is through torque control. So we want our torque control to be as repeatable as possible so we can get the correct clamp force to keep our parts together in its fastening. And so what typically will separate one type of tool from another type of tool is the torque limiting technology that they're using. And some brands or some types of tools will perform much better in a certain scenario than others. And that comes down to the components that are used, the design of the clutch or cam mechanism that is used. And so all of this kind of plays into what separates different tools from one another or different companies and different philosophies as it relates to how to implement the torque limiting technology. And so when we look at factors for selecting hand tools, obviously the application is going to dictate the requirements. And so if you have a very safety critical type of application, you may want one tool to perform that operation. And then if you had another that wasn't that critical, where your accuracy levels can be a little bit higher than they normally would be for a safety critical type of application. So that would be one type of application that's going to dictate that. Another could be the actual fastener type that you're using, whether that is going to be a self-tapping type of application or if it's going to be a security patch in that scenario. And so there are different fasteners that may require the selection of different tools. It's going to be the safety quality standards that are used with that. And that could be the actual environment that the tools are used in, the products and applications that the tools will be used in and on. And so those are some other factors to consider. So there are a number of different ones that, or different applications that will steer us into which is going to be the direct or the best application use of that particular tool. Now, tools come in either a preset or an adjustable style for hand tools. And we'll talk a little bit more about that here in just a second. Another factor is going to be the ergonomics that are going to be involved in using a particular tool in a certain orientation or a certain application. And now to talk about the preset and adjustable hand tools. You could tell a preset tool because the tool itself has no graduated scale on it. So the tool does have a range, and that tool is settable in the range of the particular tool. And that is set internally. And then the tool is verified and checked on a torque analyzer. And so that tool is being able to be used with, basically you give the operator the tool. The operator has no need to make any adjustments to that. And because it's set internally, they don't have access to be able to make any adjustments as they see fit to the application. And we're looking at getting the same repeatable torque from that particular tool on a particular application. Now, an adjustable tool obviously has a graduated scale on it. And that scale could be stamped onto the body, or it could be a digital scale within the operation of using that particular tool. And so this is going to give you a little bit of flexibility as it relates to the different torque values that you may be able to achieve through a particular requirement for a build. It's also going to give you the ability, obviously, to change that externally. And it's also good for any type of field service or an OEM kit where those particular tools may need different torque values throughout the range of the tool to be used. And so that is the adjustable hand tool. Now, when we look at torque screwdrivers, the quality standard that we use at Mountz for our tools are going to be the ISO 6789 tools. This indicates that we have a plus or minus reading of 6% of the setting, and that the tools themselves must remain in calibration for at least 5,000 cycles for that to be considered an ISO 6789 tools. Now, some of our hand tools and primarily all of our torque screwdrivers, we will guarantee a 20,000 cycle rate on those particular drivers. We'll talk a little bit more about that here in just a minute as well. Now, as I mentioned earlier, the difference that separates one brand of tool to another brand of tool is going to be the components and the design. And the design of the clutch mechanism is kind of the difference that we'll highlight here with a few different styles of drivers. But the clutch mechanism is going to give you that ability to have a really nice accuracy and consistency of torque delivery. And, there are different drivers, screwdrivers that the ones that we'll highlight here use a ball clutch type of cam mechanism, but there are some other drivers that may be inexpensive that use a plastic cam. They could use a tab that flexes to provide torque. And so when you look at the actual tool itself, it may help to know how that clutch is functioning with that. And our whole way that we handle the torque delivery is through spring compression. And so when we use the constant spring rate to develop what a torque specification is going to be based off of the spring compression that we're using, this is what we're doing when we're looking for torque. So we're compressing that spring to a certain value, and then the spring gets reset. And so if we look at some of the popular drivers that are out on the market today, if we look at this first cam mechanism, what you'll notice is we have 3 ball bearings that sit inside this race sleeve. And those ball bearings, when the tool is turned, will try to move to the next lobe. Once that happens, we're compressing the spring here, and that would give us our spring compression and our torque value. Now these would basically go from one lobe to another lobe as the tool is being used. And again, these are all ball clutch type of cams. In this scenario here, we've got 2 ball bearings that are fixed, and then we have it kind of hop over these rods within the mechanism compressing the spring here. And similar here, we've got the spring is being compressed by, again, ball bearings within a race sleeve. And there are more of them, a little bit smaller, but nevertheless, that is what we're looking at with this style. And then finally, we have, again, a ball bearing that is fixed, and then a rod here that will come and will compress and push down on the spring to give us the torque that we're looking to achieve. And so that's how a lot of drivers may be out on the market here. Now for our design, we use a little bit different design. We use a radial cam design. So we have 3 ball bearings that are in a spring housing. And as the tool is rotated, those ball bearings get pushed in and then push on a master ball bearing that is connected to a thrust bearing and is compressing the sleeve, or compressing the spring. And so that is a little bit different than using the ball clutch system, where the ball bearings are necessarily hopping over a rod or stud. In our case, we have a lot of continuous movement of the ball bearings. And so the wear factor is greatly reduced because of that. And we get a nice smooth cam operation for those particular tools. Now, if we look at the different drivers that we supply, our standard FG screwdriver is one that we sell quite a bit of, and those have a range from 3-inch ounces all the way up to 125-inch pounds. So for general fastening applications, these are going to be the standard tool that you could use. Now we'll talk about some of the unique applications for some of these tools, and one of those is going to be our one-way clutch screwdriver. And so what this means is that it will only torque in the fastening direction. And so if the tool is in the reverse direction, it remains positive. So it won't clutch out. And this is really good for any type of service that may need to be done on a particular application. These are helpful in a lot of service centers where a part will come in and they will need more torque to unloosen the fastener that they're trying to remove. And then if they go back to torque that fastener, it will give them a torque to achieve there. So the one-way clutch is one application. Again, that can be used in service or field service to give you positive in the reverse and torquing in the torquing direction. Next is going to be an impact-free driver. And what this does, it gives you for really sensitive type of applications, and those could be delicate electronic components. It could be delicate ceramics that you might be dealing with, but any type of shock or vibration or something that you want to mitigate against, we have an impact-free. And in this case, we've eliminated 3 lobes within the cam. And so we have a much greater travel of the cam mechanism that gives us a much more smoother and impact-free torquing. So this, again, would be used in those types of special applications. And then we also have clean room screwdrivers. Now, the clean room drivers are basically designed to be handled. They have a low outgassing powder coating with high performance wear resistant internal seals, and also a protective polyurethane sleeve to help trap any particulate that may be generated from the tool. But we also use special greases within those clean room tools, and there are a couple different options that are available. If a clean room is what you might need, then we have that type of screwdriver available for you as well. And then finally, we have ESD screwdrivers. And these are used obviously in electronic operations where you need a tool that has really good dissipative features. And in this case, ours has a high grade dissipative coating, again, with the high performance wear and internal seals in that particular tool. So that would be some of the screwdrivers that we offer, and depending on what your needs might be, we can provide you information on that. And so here's some of the tools that that I have here. We're going to go ahead and show you basically how the internal mechanisms are set for a standard screwdriver. So this is our FG driver. If I go ahead and I put this onto the torque tester, we have a transducer here. It has an internal reading of, or it goes from 5 to 50 inch-pounds. For that, it allows us to set a target, set our tolerance, and then it's going to give us our min and max thresholds. And so all of the readings that would be acceptable are going to be in the green area. Anything lower is in the yellow to orange area, and then anything over that is going to be the red area. So let's go ahead and we'll go ahead and see where this tool is set. So we're at about 18 and a half or so. And if we want to get to our target of 15, then what we would do to set this internally is we do have a cap that's on the end of the tool here. And we have our tool to remove that cap. And then down inside here, it's going to be almost impossible to see it because of the lighting. But we do have a small little set screw inside here. And all we really need to do is take that set screw, and we just need to turn it a quarter turn just to loosen the adjustment mechanism. And then we take our key in here, and then we'll put that into the tool. And if I turn the adjustment key counterclockwise, it's going to reduce the torque. If I turn it clockwise, it'll increase it. And so let's see where we're at after I've reduced it a little bit. So we're right at about 13 or so. So let's go ahead and adjust it back up. And so at this point, it's just a matter of fine-tuning the actual rate that we're allowing the spring to be compressed. So I've gone a little bit too high. All right. Well, we're well within our tolerance range. However, we could spend a little bit more time in getting this dialed in exactly where we want it. But that is basically how you can internally set or check the actual internals of a preset style of screwdriver. And again, these screwdrivers come in the actual the ESD version of the tool, the FG. Also comes in the clean room version. This is the clean room of the adjustable digital tool. And then we also have the larger clean room tool with the polyurethane sleeve. But to show you kind of how the we would set a digital scale tool for our FGA, we just simply power the unit on, and I think you can see that there. And so it's going to give us our value. And to make adjustments here, we can just unlock the adjustment tool, and then we can either turn the tool up or we can turn it down. And so we were at about 40 inch-pounds or so, and now we've set it down to 37. If we wanted to use a different unit of measurement, we could simply scroll through the different units. So now we're in kilogram for meters, and then we're in Newton centimeters, and then Newton meters, and then finally back to inch pounds. And so that's how you would set the adjustable screwdrivers for that particular operation. And so you can go ahead and use those for that. So that's how we would use those particular tools, and they would be in the family or product that you may need depending on your particular needs. So, all right, now we'll go ahead and we'll move on to the torque screwdrivers, or excuse me, torque wrenches. And so there's a lot of different torque wrenches that are available as well. There are dial torque wrenches, split beam torque wrenches. There are digital torque wrenches, cam over and click wrenches. So depending on what application needs, again, you might need one wrench may be working better in a scenario than the other. And so let's talk about three of these styles of wrenches. And the first one we'll talk about, first we'll talk about the standards. Again, the 6789 ISO rating. We're looking at torque wrenches that are under 10 Newton meters. Those are plus or minus 6%. And then any wrench that's over 10 Newton meters is plus or minus 4%. And again, the ISO specification is 5,000 readings within the cycle for to make sure that those still qualify as an ISO 6789 tool with that. And so now we'll move on to the click wrench. So the click wrench is by far the most popular torque wrench out in actually the world. One, they're very easy to use. They're easy to set. They are very inexpensive, but they do come with a price as it relates to how they are being used. Now, a click wrench is very operator dependent, meaning that depending on how you pull that wrench is going to determine where the torque ends up. Now, where the wrench clicks is one area or one value, but where the operator stops pulling is the second operation. And when the wrench clicks, you typically only have about 3 degrees before you're starting to add positive torque to the application. And so as you use that tool, you have to be very deliberate and very controlled when doing that. If there are operators that will go very quick with a click wrench, you're adding a tremendous amount of over torque to that. Or you see operators that may double click or triple click. again, you're adding additional amount of over torque to that. And we'll look at that here in our operation. And so graphically what that looks like is as torque is being applied, the wrench will click at the torque value and then will have 3 degrees of deflection, and then you're adding additional over torque. And that's what that would look like graphically. So another style of wrench that we have available is going to be a breakover style of wrench. Now this wrench does give you the ability to have a much better control over the torquing process and give you a much better signal as when torque is achieved. And so how we use this is we have an indication mark on where to hold the tool. And as you apply torque, once the head begins to break, then you have reached your torque value. Now the full break on that can be anywhere from 20 degrees to 45 degrees, but there is a clear indication that you have reached your torque value. The other really nice thing about the breakover style of tool is that there are many types of heads that can be used with different or with the same tool, and you can interchange the heads if you wanted to, or you could have a fixed head on there. But they can have open end heads, they can have box end heads, they can have flare end heads, you could have Allen keys in there. And in some cases, if you have a very difficult, hard to reach type of place, we can use a custom bent different heads in there to satisfy that with the breakover style of wrench. So a very flexible, very nice and accurate type of tool to use. And so if we look at this graphically, what we've done is we increased the amount of deflection that we have to make sure that we stop pulling on that wrench to help avoid against any additional over torque that may happen during the actual operation. And so that would lead us to the cam over style of wrench. And so this style of tool acts very much like a torque screwdriver, meaning that once that wrench cams, it's reset, and there's not the ability to add over torque the same as you would with a cam mechanism on a torque screwdriver. And so with the cam over style tool, again, this is an internally preset tool. It does give us the ability to take that wrench, and when it cams over, we've hit our torque value, and there's no way that we can add additional torque to the process. And so if we try to hit that same fastener with the cam mechanism again, it's not going to over torque at all, because it's going to come up to the torque drop, and then it'll come back up, and we can see that what it looks like in a graphic here. So as we apply load, we hit our torque value. The system will then reset the cam. We can try and cam it again, and we have prevented over torque. And so in those real safety critical type of applications, this is a fantastic type of wrench to use, where you can just give the operator the tool to use, and you don't have to worry about them adding additional torque to the actual application itself. So in the way that we're compressing the spring here with this tool is you can see that we have our cam, and as it is rotated, it's pushing in on the spring, and then the cam itself resets. And again, making a very, very accurate type of application process. So if we kind of break these down in different categories, we would have our click wrench, which is not so good at being able to guarantee a final torque accuracy, not very good with error proofing. The real advantages are the price and the torque ranges that are available. You can go very, very high in the range of a click wrench. And then next would be the breakover wrench, which has good final torque accuracy and very good error proofing. And it does have a little bit more expanded range than the best option would be the cam over wrench. So the cam over wrench gives us really good final torque accuracy, gives us error proofing, and it does have issues when we're looking at trying to use that in a higher torque range type of scenario. Now, we didn't touch on a digital wrench, but a digital wrench is going to signal when the torque is actually achieved. But again, it doesn't guarantee at where the operator stops pulling it. So it acts similar to a click wrench in the fact that you're still reliant on the operator to stop pulling when that signal is achieved. So we didn't necessarily highlight that here, but I just wanted to make a note of that. And that's going to lead us to our poll question today. And so we can go ahead and launch that poll. And so we're looking at what type of mechanical hand tools are used in your facility. And we'll give you a couple or a few seconds here to go ahead and answer that. And then I'm going to grab a drink of water and go from there. All right. Thanks very much for that. It is a mix of mostly a mixed variation of hand tools, followed by torque screwdrivers and then breakover wrenches. So thanks very much for participating in that. And we'll go ahead and move on to our demo of the hand tools. And so what I have here, again, the same analyzer. And let's go ahead and take a look at the different torque wrenches that we have. And so, as I mentioned with the click wrench and its ability to be very operator dependent, we'll go ahead and show that here. And just so you're aware, how this basically works is once the wrench clicks, you've hit your torque value. And if you look at this rivet point here or this pin, it is connected to this head mechanism that is down inside of the tube itself. And in here is a little block that will actually go on its side. And that is what is allowing the head mechanism to hit the inside wall, giving us our click mechanism. Now, there's a couple different other styles of click wrenches, but primarily this is the click wrench that you would see. But they all kind of work in the same process. Now, one thing to keep in mind here is because our fulcrum point is inside the tool, any change that we make to where the wrench is being held is going to change the torque output of the tool itself. So if we were to hold the tool up here, we would be increasing the amount of torque. And that can certainly be seen when we make any adjustments to the tool. You can see if you do tighten this, we're actually shortening the wrench because it's designed, the handle is for you to hold it in the correct spot. If we added an extension to this, we would be decreasing the torque output because the fulcrum point is inside of the tool. As opposed to the cam over wrench, which is a non-link dependent wrench, meaning we can hold it anywhere up and down the handle, and it's still going to give us the same torque output. And we'll look at that here as well. And so with this, this tool, I think it's set to about, again, same 15 inch-pounds. But what I want to highlight here is we would use this operation in the first peak mode. And this is typically how calibration facilities will calibrate their tools. They'll put a torque analyzer in the first peak mode because what it's going to measure is where that click happens, and it would basically ignore any type of over torque that may happen with that. And so if I use the tool, you can see here that it clicked let's make one adjustment here to disable the clear feature. If I go ahead and click the wrench, you can see the wrench clicked at 14 inch-pounds, 14.7, but we ended up at 30 inch-pounds. So if an operator, again, is pulling the wrench without being very deliberate and smooth, we're adding additional torque to the wrench. And so if I go slow, you can see 14.72, 14.72. We get the same kind of consistent results. But if I were to double click, you can see that we're adding much more additional torque to that application. And so the savings that you might get from the tool being less expensive may not be worth the risk of a fastener that may be over torqued. So nevertheless, that is how a click wrench would be used. Let's move to the breakover wrench, and let's set our target torque to 8.5 inch-pounds. And so in this case, we have our breakover style tool with a box end head. And as we apply torque, we have this ring here. This is where we need to hold the tool. And then once the wrench begins to break, that is when we've hit our torque value. Now, if we were to go to the extreme, we would have to break it over more than 45 degrees and keep going to add any additional torque to the unit. So let's change this to peak mode. And that's going to measure the highest peak torque generated. So as I pull the wrench, you can see as it begins, well, you really can't see it breaking. Let's see. Let's move this out just a little bit. A little bit more. There we go. And then you kind of can see it here on the edge. As the wrench begins to break, that's when we've hit our torque value. And that is how that would function with using this style of tool. And again, you can have different heads that can be put on these tools. And we have different ranges as well. So those were our TBIH wrenches. And then we also have our TBX series, which is does give you that same type of breakover mechanism that you can use. And now we can take a look at the cam over style wrench. Again, as this wrench is used, it will simply slip and cam over, and that gives us our values. And let's see where this wrench is set. So a little bit higher on this end. So let's go to 26 as our target. And so if I try to come back and hit another cam, you can see that it's not adding any additional over torque to the actual operation. Now, if we want to look at this graphically, we can do that, and we can put a target in here. And what you'll see is as the tool is being used, it comes up and the then cam resets, and so we don't have the ability to add any additional over torque to that. In the case of the click wrench, let's see, I think we were set somewhere around 14 inch-pounds. Turn that on. You can see that our wrench is clicking in the target area, but we're adding an additional amount of over torque, in this case 30 inch-pounds for that. And so if I were to pull this very smoothly and with intentionality, you can see that I can keep it within the target area. But if I double click or triple click, you can see that we're adding much more torque to the fastener with the click wrench. Again, a very operator dependent type of tool, as opposed to the cam over style tool or the breakover style of tool. And so with that, that is going to bring it to the end of today's presentation. So if you have any questions, feel free to put those into the chat and we can go ahead and talk about those. So I'll give you a second to do that. And if those had happened earlier. So Chris, do we have any questions?
Hello, Dave. We have a couple questions here. One was, when you're calibrating like a screwdriver or a wrench, is there a reason why you would apply load to the tool before the calibration process?
Yeah, typically when you're doing a calibration or setting a screwdriver, you're going to want to exercise it about 5 to 10 times, or cycle it 5 to 10 times. That way you get the components kind of working and get things moving a little bit in a scenario, kind of warming up the tool or breaking it in just to make sure that your readings are consistent with whatever calibration procedure that you're using. So yeah, you typically want to cycle the tool at least 5 to 10 times.
All right. And then another follow-up question on that part was, when calibrating a tool, is there a recommendation number of test data readings to use?
So typically it's going to be 5 points, depending on or 5 cycles, depending on the calibration. There are different certificate levels of calibration and different standards for what you may need or what your organization might want as far as if it's going to be an ISO 67897 or a 17025 type of test, or if it's going to be a different validation. But standard typically is 5 readings.
All right, Dave. I think that's all the questions we have for today then.
All right, fantastic. Thank you so much for joining us today. I hope you join us for our next webinar that will be here next month. So with that, have a great day and we'll see you soon.